SwayamPrabha. Digital India. Educated India.
Okay, so we will continue our discussion in this lecture. That is, we are still in bending of sheets, and in the previous section, what we discussed is basically summarized here. So we evaluated strain distribution, okay, for bending of sheet with both moment and tension, okay, and then we evaluated epsilon 1, so which is nothing but epsilon A plus epsilon B, and then epsilon B can be approximated to 1 by rho, which is actually ln of 1 plus 1 by rho, and can be approximated to 1 by rho. So this is what we have seen, and then in that case bending without tension, so we have evaluated two important things. One is stress distribution, other one is moment versus curvature diagram. We got both of this, which means given strain distribution, okay, that is bending without tension, which means that is a specific case of what we derived for epsilon 1 and epsilon 1. So in which basically epsilon A would become 0 in this case, bending without tension. So we have epsilon B only. So for that we got stress distribution. To get stress distribution, then we have to relate your flow stress to strain. So in that case we discussed 3-4 important models, okay, relating stress and strain, and then we evaluated a moment for each case, and then we drew a diagram, moment versus 1 by rho diagram. So in that we saw actually 3 cases. One is elastic bending, rigid perfectly plastic, other one is a strain hardening sheet. These 3 were discussed in the previous section. So elastic bending means what would be the relationship between stress and strain, then what will be the stress distribution, what will be moment 1 by rho diagram, and rigid perfectly plastic what will be the case, and general one which is a strain hardening case, what would be these two. Okay, this is what we discussed in the previous case. There is one more case in this, okay, that we will see, but before that, okay, let us quickly discuss what we discussed as a last section, which is nothing but your strain hardening sheet. Okay, strain hardening sheet, we know stress sigma is equal to k epsilon power n in general, and with respect to bending we say sigma 1 is equal to k1 k dash epsilon 1 power n, and epsilon 1 is nothing but y by rho. This way we can get, and of course we can directly draw this stress diagram across a section, which is what is given here. This is little different than what we gave in last class. Okay, for the same situation there is little non-linearity here. Okay, you can see that, and it will drop to the negative values in the second bottom half of the sheet. Okay, and this change has to be noted. Okay, and moment 1 by rho diagram is also shown here for the strain hardening sheet. This is what we have discussed in the last part of previous section. So now we will work out one problem later on using this bending of a strain hardening sheet. At that time you will again use this type of relationship. Okay, so now let us go to the fourth case, okay, that is elastic perfectly plastic bending. Okay, so whatever we have seen are basically elastic bending, rigid perfectly plastic bending, and the strain hardening sheet. Okay, so now there is another case where we are going to see EPP. It's called elastic perfectly plastic bending. Okay, this model we have already discussed. Okay, we already discussed. So it basically, this elastic perfectly plastic bending, it basically uses elastic perfectly plastic model, which we already discussed. Okay, and the model is actually shown in this figure. This is the same figure, okay, which is drawn between sigma 1 versus epsilon 1, and you have the elastic part and then a constant flow stress plastic part, which is nothing but S. So when sigma reaches S, when sigma reaches S, that is at this particular stage, at this particular transit, you will see that there will be change in your stress strain relationship, which is nothing but sigma 1 equal to S. Less than that particular stage, you will see that sigma 1 is equal to E dash into epsilon 1 is what we have seen. Okay. So, but this elastic perfectly plastic, okay, before that we have seen elastic bending. Okay. In bending we have seen only actually 3 cases right now. In that, first case was elastic bending, in which we took only the first part of the curve. Now as the heading here suggests, it is elastic perfectly plastic bending, okay, which means that it is suitable for curvatures beyond 1 by rho E. That is a limiting case of 1 by rho. Okay, that is a limiting case of 1 by rho, and 1 by rho E we have already evaluated in the first case. If you go back to your previous one, you can say that 1 by rho E is this much, 2S by E dash T, 2S by E dash T. This is what we evaluated, right? So let us come back to this. For the curvatures more than 1 by rho E, beyond 1 by rho E, but below where moment reaches MP, then this model can be applicable. Whatever we are going to discuss is applicable. Okay. So it is not fully MP, it has not gone to that state, but then it is suitable for curvatures beyond 1 by rho E. So if that is a situation, okay, then this type of elastic plastic bending can be seen. Okay. So for this, a model is shown here, which we already discussed. So if you want to get a stress distribution for this, it would be like a combination of your elastic bending and perfectly plastic, rigid perfectly plastic bending, right. So in the elastic bending, in the previous section we have seen this as a stress strain distribution, right. So your this one is your stress distribution, right. So in rigid perfectly plastic, you will see this S, there will be a constant S, okay, and then that we call it as rigid perfectly plastic. Now it is basically a combination of these two, elastic perfectly plastic, and you will see this would be the stress distribution. That means up to a particular, this is anyway T by 2, up to a particular distance y from the mid surface, okay. So you are going to have the elastic representation of elastic part, and then it will become plastic part where the flow stress would be equal to plane strain flow stress, which is nothing but S. So when you see from upper part of the sheet, when you start from here, so you will have of course this is the uppermost fiber will reach S first, okay, and then you will see that it will be a constant up to a particular you will have a flow stress of S up to a particular thickness, and then below that you will see that it will be an elastic part, it will reach 0, and on the bottom side it will be just reflection of that, an opposite to that. Okay. So now what we are saying is this particular transition is what is called as YE. YE means in general any distance from the mid surface, so we are calling it as YE here, okay, because this is a limit of your elastic part, elastic representation, this part. Okay. So now for the case Y greater than YE, the material is plastic with the flow stress equal to S. That is what we have written here. Okay. For a case Y greater than YE, okay. So if you have a situation like this, the material will become plastic with a flow stress of S. That is what is given in this stress distribution. Okay. So similar distribution we got from in strain hardening sheet also. Only thing is it will become little non-linear, okay, in its variation. That is the only difference. So stress distribution of elastic perfectly plastic bending is this. So now we can calculate this YE. This because this transition is going to be important. In the previous two cases, elastic and RPP, rigid perfectly plastic, there is no such transition, but here this transition happens, YE. Okay. This YE can be calculated from simple equations which you already know. Okay. So we know that this epsilon B is nothing but ln of 1 plus y by rho. Okay. So in this case only epsilon B exists, 1 plus y by rho is approximately equal to y by rho. Okay. So this y by rho, you can see that it is nothing but S by E dash. Okay. So your y by rho, you can say that it is nothing but S by E dash. Okay. So from this we can get this y, which is nothing but my YE if we put some condition to that, if you put some condition to it. So your y by rho, you can see that this equation is already known to us, isn't it? This equation is already known to us. On the right hand side I have your y by rho, suppose y is here, y by rho is sigma 1 by E. So, y by rho is sigma 1 divided by E. Sigma 1 is nothing but, in our case it is E dash. Okay. Sigma 1 is nothing but S actually, to S by E dash. So, we can directly write this equation, y by rho is equal to S by E dash, which is going to give you ye, which is nothing but S by E dash into 1 by y by rho. Oh. So, ye is nothing but, I am going to take rho on the right hand side and I am going to write 1 by rho, because 1 by rho is what is generally we refer. No? So, 1 by y by rho. Okay. So, this S by E dash, okay, this S by E dash is nothing but, this ratio is nothing but T by 2 into 1 by rho, isn't it? So, S by E dash in this equation is nothing but T by 2, okay, into 1 by rho. Okay. So, into 1 by rho. So, which if I put it in this equation in place of S by E dash, so you will see that it is going to be T by 2 into 1 by rho. Okay. Since I am going to put ye here, I am going to say 1 by rho E divided by this 1 by rho will come. Okay. So, this part is actually S by E dash. This part is actually S by E dash. How do we get from this? So, T by 2 into 1 by rho. So, I am putting a limiting case here ye. So, I am going to put a limiting case here 1 by rho E. Okay. So, this entire thing, this particular ratio, this one is I am going to call it as m. So, I am going to say m into T by 2. So, ye is nothing but m T by 2. Of course, T you know is nothing but the original thickness of the sheet, and m is this particular ratio 1 by rho E divided by 1 by rho. So, 1 by rho is actually a reference for us. 1 by rho, 1 E is nothing but a limiting case. So, 1 by rho is nothing but the radius of curvature which should have been given to the sheet, and 1 by rho E is nothing but your limiting case 1 by rho E. This ratio I am going to call it as m. This m has nothing to do with any other m which we have discussed before. So, let us not get confused with this. So, this m can vary between 0 and 1. This m can vary between 0 and 1. Okay. So, in this way your ye here can be calculated, which is nothing but m into T by 2, and m is nothing but it is a ratio of basically 2 radius of curvature 1 by rho E divided by 1 by rho, curvature 1 by rho E divided by 1 by rho. Okay. So, a simple question can be asked like this: evaluate ye. Okay. Ye, that means the transition between this part and this part. Calculate ye for a material which follows elastic perfectly plastic bending means. So, we can say like, we can go back to this original equation, and from here basically we can get ye. Okay. So, now for this particular case you can also get moment. So, now the moment is basically the general equation is m is equal to integral. So, we can say basically like minus T by 2 to T by 2 sigma 1 y dy, sigma 1 y dy, right. So, minus T by 2 to T by 2 sigma 1 y dy. So, now here what we are going to do is, we are going to say that if you want to get moment, so we are going to divide that into two parts. We are going to divide that into two parts. One is from the mid to the transition happens, that is ye, and from ye to the uppermost layer, that is your T by 2. This is the way we are going to divide this. So, this is one part for integration, this is another part for integration. So, the limit changes actually. Okay, the limit is going to change because situation is different. So, anyway I am putting 2 times here because it is symmetric. So, 0 to ye is one part. Okay. So, which is going to be my sigma 1 y dy. So, in this case sigma 1 is nothing but this fellow y dy. So, E dash into y by rho, isn't it? So, sigma 1 is nothing but E dash into epsilon b. So, which is nothing but my E dash into y by rho. So, y dy will remain as it is, and in the second part you will see that it is going to be equal to s. So, sigma 1 is nothing but s. So, I will say ye to T by 2, ye to T by 2 s into sigma 1 is nothing but s y dy. So, you can integrate it appropriately and then put limits, you will get s T square by 12 into 3 minus m square. So, this is what you get generally. So, you can look into it, and like previous cases, we can also have m versus 1 by rho diagram. So, here you will see that it is again a combination of your the elastic bending and perfectly plastic part of rigid plastic bending. You can see that. So, this is your straight line, then a small transition, and then you are going to have the horizontal part. Okay. So, this is a moment 1 by rho diagram for EPP bending. Okay. So, and this is going to be your ME. So, ME we already discussed as ST square by 6, we already derived this. ME is nothing but ST square by 6. If you go back to previous one, you can get it. ME is ST square by 6, isn't it? So, ME is ST square by 6, yes. Okay. Your limiting elastic moment, okay, is obtained MET square by 6. Similarly, we got MP also, which is nothing but ST square by 4. Okay. So, these two can be combinedly used to draw this particular moment versus 1 by rho diagram, ST square by 6, ST square by 4. Okay. And we also previously derived that MP by ME is nothing but 3 by 2. So, I can write this as 3 by 2 ME. I can write this as, so you can say ME. So, this would be ME means this is 3 by 2 of ME is nothing but ST square by 4. Right. So, in this way we can interpret it like it is understood from the figure, this particular figure, for a non-strain hardening material, okay, for a non-strain hardening material, the moment still increases beyond ME and reaches 1.5 times of ME and becomes constant after that. Right. So, the moment still reaches beyond ME. So, ME is this particular value, that is a small transition, and then it becomes 1.5 ME. So, this height it becomes 1.5 times ME, okay, and then it becomes constant. Okay. So, though there is no hardening, there will be slight increase in your M, that is your 3 by 2 times of ME if you want to push it to a constant moment. So, that much is required here. So, that is one interpretation one can get from this. So, now let us go ahead in developing a simple model for theoretical model for spring back. I think we discussed in the previous section itself that it is moment without tension. Again we are going to see. So, you are taking a bent sheet first and then you are taking an unbent sheet. So, since there is no tension, okay, only moment is given, okay, there will be a change in curvature and bent angle in this way. Theta becomes theta plus del theta, rho becomes rho plus del rho, okay, and the length of the mid surface is given by L is equal to rho theta. So, this L is nothing but rho theta. Okay. This L length will remain same, will be unchanged. Why? Because there is no tension given here. This length will remain same, okay, and so it can be written as theta is written as 1 by rho times L. Okay, and if you differentiate it by keeping L as constant, we can say del theta by theta is nothing but del 1 by rho divided by 1 by rho. So, this del theta, which is nothing but the angular change when you bend a sheet, the angular change due to spring back is given by this delta theta, which is nothing but your theta into del 1 by rho divided by 1 by rho. So, either you calculate this or you calculate this, we can calculate the spring back, Okay. So, this we already discussed, I just refreshing it here. So, now let us go to the spring back in an elastic perfectly plastic material. Let us go to this particular case. Okay. We are going to see only one case and we see how a simple model, theoretical model for spring back can be evaluated in this. So, elastic perfectly plastic EPP, we just now discussed it. We just now discussed of how would be your stress distribution, how would be your moment curvature diagram. We have just now discussed. Okay, and for this spring back in elastic perfectly plastic material, we are going to use a similar model which we have already discussed, and a similar stress strain diagram is drawn for this particular case, but with reverse loading. Okay, both are shown here. So, you will see that. So, you are starting from here and you are moving like this. Okay. So, then once you have a slope of E dash, then you reach this particular point before it becomes the flow stress becomes S, that becomes a start of your plastic deformation, and then it goes on, but then when you unload it, it comes like this, and then you will see that you can further deform it to reach this particular stage to get S. Okay. So, this can be drawn in this way, the blue line and orange line. Blue one represents the tensile part, and your orange one represents the compression part. Okay. I mean the reverse loading part. Okay. So, in this case you will see that this particular is height is S, or the value is S flow stress to reach plastic state, and in the opposite case you will get generally minus S. Let us keep it like that, and these two are equal, okay, which means that we are not considering Boschinger effect. We are not considering something called as a Boschinger effect. Okay. So, in the tensile part of deformation and in the negative part of deformation, if this stress, flow stress or yield stress S remains same, then we say that the Boschinger effect is not considered. But if you consider some softening in the negative side, suppose this is not S, this is not minus S, this is less than S, let us say, this is less than the first time flow stress, that is your S, then Boschinger effect is considered. But we are not going to consider it. We take a simple case without considering Boschinger effect. We can say that the change in stress is given by minus 2S, okay, before it reaches the plastic state. So, which means that you need a change in stress of minus 2S to make that material to reach plastic state, which can have flow stress, plane strain flow stress of S. That is the meaning of this particular diagram. Okay. So, now what we are going to do is we are going to use our previous equation which we already know. Okay. So, we are taking a case that unloading part is elastic in nature. Okay. So, this unloading part is basically elastic in nature, that is why we say that it is a parallel to the elastic part. Okay. Unloading part is elastic in nature. The elastic bending equations which we wrote before can be written in this way also. This equation is known to us, m by I is equal to sigma 1 by y is equal to E dash by rho, which is known to us. This can be written as del m by I is equal to del sigma 1 by y is equal to E dash into del 1 by rho. We are somehow bringing in this del 1 by rho, which is what we are going to calculate it to quantify spring back. So, this is the fellow which we need actually to be calculated. Okay. So, this same equation has been modified as del m by I is equal to del sigma 1 by y, del sigma 1 by y is already given, is equal to E dash into del 1 by rho. And what is E dash? We know that it is plane strain Young's modulus. So, now if we want to get del 1 by rho, okay, we need to know one more thing here. Now, what we are going to do is unloading is an elastic process. By considering that, we are also going to assume one more thing, like a case in which, assuming that the sheet is bent to fully plastic moment, okay, it is already gone into fully plastic moment, okay, and unloading is done. Unloading will be parallel to the elastic loading line as shown in this particular figure. This particular figure is moment 1 by rho diagram, which we have just now seen. Okay. So, for EPP bending, elastic perfectly plastic bending, you will see that the same diagram, you have a elastic and then transition and then a fully plastic part with a height of MP. Okay. So, now you will see that we are going to unload it from this particular point. Okay. Unloading is done here, and you will see that when you unload it, actually we need to get this particular curvature 1 by rho naught. 1 by rho naught is actually the reference. 1 by rho naught is actually the reference that we need to convert the sheet to. Okay. But this del 1 by rho has happened because you are unloading it, and which is what we are going to, we just now encircled it, del 1 by rho. This fellow, this fellow which we just now discussed is actually represented in this diagram, which is what is responsible for our spring back. Okay. So, 1 by rho naught is a reference for us, okay, but it is not going to happen that way. So, there is going to be some change, that is del 1 by rho, which is what we need to quantify, and all other things are known to us. This is me st square by 6, and you are removing moment from a fully plastic moment situation, which is nothing but MP is the ST square by 4, which is nothing but 3 by 2 m, which we already know, 3 by 2 me. Okay. So now from this figure I can directly write this del 1 by rho divided by 1 by rho e will be equal to my minus MP divided by me, minus MP divided by me. Okay. So similar triangle, okay, that particular concept we can use, del 1 by rho divided by 1 by rho e, nothing but my minus MP divided by this me, up to this particular stage, up to this. Okay. So now because I am unloading the material from fully plastic state, okay, which is nothing but my MP is going to come, I can simply say that this MP is nothing but my delta m. The change in moment is nothing but my fully plastic moment only, which is nothing but my MP. Okay. So this minus MP is nothing but your del m. Directly we can write that because I am going to fully unload it, unloading the material from a plastic moment, from a fully plastic moment, so that the change in moment is nothing but my MP itself. Okay. So this equation conveys these many points for us. Okay. And this is already known to us. Okay. So my MP by ME is nothing but 3 by 2, also given here ST square by 4 divided by ST square by 6, which is nothing but 6 by 4, is nothing but my 3 by 2. Now it is very straightforward. So I want this del 1 by rho. So del 1 by rho is nothing but my 1 by rho e into minus MP by me, okay, which is nothing but 1 by rho e is already we derived this 2s by e dash t. 1 by rho is a limiting case, no? Limiting case for your curvature. Okay. When we derived me, we also derived 1 by rho e, which is nothing but 2s by e dash t into minus 3 by 2 will give me, okay, 2 will be cancelled, okay, minus 3s by e dash t, which is nothing but my del 1 by rho. So del 1 by rho is nothing but minus 3s by e dash t, which is a simple equation to calculate the change in curvature because of spring back for a material which is following elastic perfectly plastic bending, and unloading is done in fully plastic stage, fully plastic moment. So that is why I have written clearly here, this is M1 by rho diagram for EPP bending showing unloading from fully plastic moment. Okay. And for that particular case you can use this particular equation. So now it is all about slightly simplifying this. Okay. We can also write this because my del 1 by rho is known to me, del 1 by rho is known to me. So from the previous equation, del 1 by rho is nothing but you take this way. So your del theta by theta would be there, and 1 by rho will go to the left hand side. So I can directly write this as del theta by theta is nothing but minus 3s by e dash t into rho naught I am keeping, instead of just rho I am just keeping it as rho naught. So this way I can calculate my change in theta, okay, or change in 1 by rho that is actually responsible for spring back. So it is a very simple equation, but not a fully accurate one, for a simple reason that does not include strain hardening, okay, does not include strain hardening. And I was previously telling you that though we are discussing spring back in terms of during bending, but then spring back can happen during general sheet forming process also, like for example cup deep drawing where bending is there. Okay. And in that type of processes, if you want to predict spring back, then strain hardening consideration is going to be very important for us. But here this particular model is not that accurate, but it will give you a pretty good idea about what would be the spring back, and we can understand certain things from this. Okay. And the strain rate effect is also not considered. Okay. And one simple way is you can this plane strain flow stress can be made as a function of strain. Okay. So what we have done is basically we kept S as constant. Okay. In the previous model also, the stress strain diagram also you see that S was made as constant and Borschinger effect was also not considered, though, so there is no softening because of bending, okay, reverse bending. So in that case basically in one way you can consider somehow strain hardening, okay, is by relating this S to epsilon. Okay. Somehow if you relate S to epsilon, then you can make it somehow a function of a strain hardening effect also. Okay. And it is also mentioned that the equation is valid or good only for small differences in angle or curvature. and when the sheet has been bent to nearly fully plastic state. This is what I was telling you. Okay. So, this equation is valid or good only in such situations. So, now in this from this equation we can also say that a spring back is proportional to few things. One is ratio of flow stress to elastic modulus S by E dash, correct. Del theta by theta is nothing but S by E dash. This S by E dash, I was telling you before that this ratio is very important. This is nothing but your sigma ys divided by E only, okay, yield strength to elastic modulus only, but for plane strain bending we are writing this as S by E dash. So, this ratio becomes important, and this, because these both are related to, somehow related to elastic deformation, and this ratio is of the order of 1 by 1000, that we should have some idea. Okay. Why? Because this S is generally said in MPa and E dash is generally said in GPa. So, you can say that it is about 1 by 1000, in that order you will have. And bend ratio, rho by T we introduced, only thing I am just changing the nomenclature, it is rho dash by T, and of course bend angle, of course this bend angle. Okay. So, from this simple equation one can understand that spring back is actually proportional to S by E dash and rho by T and the bend angle theta. These many items can be understood from this. So, now spring back has been evaluated, del 1 by rho has been obtained, or del theta also can be obtained from the simple discussion. Okay. So, now we are going to consider two cases. One is what would be residual stress in that section, seat section after unloading. The next one is if you do reverse bending, okay, what are the details in case of reverse bending that you can evaluate. That is what we are going to see in next two small subsections. So, now here we say when EPP sheet is unloaded, elastic perfectly plastic sheet unloaded from fully plastic state, okay, the change in moment is nothing but minus MP, okay, which we already discussed. Okay, the change in moment would be minus MP. So, now this I am going to put it in this particular equation. This equation is already known to you, just now we introduced del m by I is equal to del sigma 1 by y is equal to E dash into del 1 by rho, isn't it. So, just now we discussed about it, this particular one, del m by I is equal to del sigma 1 by y is equal to E dash into del 1 by rho. The same equation, what I am going to do is I am going to substitute MP here. So, minus MP divided by I is nothing but T cube by 12, again for unit width is equal to del sigma 1 divided by y would become, my y would become a limiting case which is nothing but T by 2. Why? Because this when you enter into plastic moment, it means that you are reaching the uppermost layer which has already reached a plastic deformation state, and that uppermost layer is nothing but T by 2 for me. Okay. So, minus MP divided by I, which is nothing T cube by 12 is equal to del sigma 1 divided by my T by 2. Okay. So, my MP is known, ST square by 4, T cube by 12, T by 2, del sigma 1. So, from this if you can calculate my del sigma 1, it will lead to a simple interpretation which is nothing but minus 3 by 2 S. So, this del sigma 1 is going to be equal to minus 3 by 2 S when you unload it. Okay. What does it mean? This equation also indicates one important thing which is given here. This equation indicates that unloading process is fully elastic. Why? Because it is 1.5 times of S, which is less than my 2S discussed before. This delta sigma 1 is less than 2S, which we discussed before. 2S is the del sigma 1 that is required, this particular figure. 2S is the del sigma 1 that is required before reaching the plastic state, that is a limit for. So, it is less than that. So, it is 3 by 2 only. So, 1.5 times S only. So, which means that it be in unloading is fully elastic. Okay. So, now what I am going to do is I am going to add this part, this delta sigma 1, I am going to add with already existing one, that is nothing but my S, which is already existing one. This can be represented schematically as adding an elastic stress distribution, that is confirmed by now. It is elastic stress distribution that is confirmed, which is minus 3S by 2 to the fully plastic moment as shown in this particular figure. So, this is already known to us. Okay. So, this value is plane strain flow stress S. Okay. And we are going to add this minus 3s by 2 at the top, isn't it? So, we are putting t by 2 no. When you put 3 by 2, you are getting minus 3 by 2 s. So, which means that it will be at the top, which will be opposite to that at the bottom. You are going to add these two, okay, which means you are giving moment and you are giving a negative moment also here. So, what will be the residual moment you have? What will be the residual stress you have here? So, if you add these two, you will get a distribution like this, which has got minus s by 2 at the top. Okay. So, it is s minus 3 by 2 s, okay, which is nothing but half, no, minus half. So, minus 3 s by 2 would be there, okay, and then you will get, you can also add this part with this part, okay. So, you will get that value here and it will be opposite at the bottom. So, this would be your residual stress distribution after unloading from fully plastic moment for EPP, elastic perfectly plastic bending. So, what interpretation you get from this? The stress distribution shows that after unloading, the tension side of the bend, okay, let us say this particular one, tension side of the bend, your T I am saying, would have a compressive residual stress at the surface minus s by 2, and in the inner surface, okay, there would be a residual tensile stress. Inner surface is this I. This is the outer surface where you have tensile. In the inner surface, you will see that there will be a residual stress which will be tensile in nature. Okay. The tension side of the bend would have a compressive residual stress, and the inner surface or the bottom surface or the compression surface would have a residual tensile stress. This is how the distribution would be for EPP material, okay, which is unloaded from fully plastic moment. So, now this is one. So, now let us go to reverse bending. Okay. So, reverse bending means you are bending the material and then you are unloading it and reverse bend it. Okay. So, this particular situation. So, your moment 1 by rho is like this. So, you are taking this part here and then it becomes a constant flow stress, you unload it and then follow this part and then again you bend it and then you take it to the negative side. So, the question is, we have seen that the change in stress required to have yielding in the outer layer of the sheet is of course del sigma is equal to minus 2s. Okay. So, now what we are going to do is, okay, now this del sigma 1 is equal to minus 2s, if you put it in this equation we know already. So, we need to see this del m. What is the value? Del m is nothing but I into del sigma 1 by y. So, I is nothing but t cube by 12. Okay. So, y is nothing but of course t by 2. Why? Because again the outermost layer, okay, will reach yielding, okay, when del sigma 1 is equal to minus 2s happens. Okay. And del sigma 1 is equal to 2s I am substituting here. So, if you do that, del m would be equal to minus s square by 3, minus s square by 3. So, when you have del sigma 1 of minus 2s, then del m would be minus s t square by 3. Okay. And the moment for reverse yielding, suppose you want to reverse bend and then you have to give some moment which will cause first yielding in the reverse side. Okay. Like we have a ME here. Okay. Once you reach ME, okay, so you are going to enter into the plastic part. Similarly, on the bottom side, what would be that value that can be obtained in this way? So, I am writing reverse bending M R E V is equal to, so earlier I am going to have S T square by 4 minus S T square by 3, that would be equal to minus S T square by 12, which if you see it is nothing but minus M E by 2, minus M E by 2. So, which is what is represented here. So, this M E is nothing but S T square by 6, this M E is nothing but S T square by 12, which is just half of M E. Okay. So, which is just half of my M E. Okay. So, this figure shows that yielding at reverse bending occurs at half the value of initial yield moment. Okay. That is your S T square by 6. Half the value of means S T square by 6 divided by 2. So, it is nothing but S T square by 12, which is nothing but M E by 2. Okay. So, you need to, in the reverse bending side, you need to give M E, okay, or M reverse bending, which will be nothing but M E by 2, only half of the first M E that you gave for the first bend. Even if you do not consider Boschinger effect, you need to give only this much. Okay. So, actual softening, if you see, would be greater than this if you consider Borschinger effect also. So, even without Borschinger effect, okay, your MREV would be minus ME by 2 only, okay, which is not actually ME, which is half of that only. But if you consider Borschinger effect, then with further softening there would be a greater softening of the material. So, the estimated value would be different than this. Okay. So, these are the two important subtopics that we discussed for EPP material. So, what we have done is actually 3 parts. Considering EPP material and unloading from fully plastic moment, we derived a simple equation for expression for del 1 by rho or del theta. Okay. So, which depends on S by E dash, rho by T and your bend angle theta. So, now if you want to calculate residual stress, then we are going to add minus 3 by 2 S, which is nothing but the elastic stress only. Okay. This part will be added to your fully plastic state, that is your S. S is nothing but your fully plastic, that plane strain flow stress, right, fully plastic state. So, if you add it, finally you get a residual stress distribution like this, and then we also calculated the M required for reverse bending, which will be just half of the ME that is required in the first bending. Okay. That is what we derived here, even if we do not consider Borschinger effect. Okay. So, let us do this small problem. Okay. A strip of sheet metal which is 2 mm thick and 200 mm wide. Okay. So, width of the sheet is given here, we can see, okay, is to be bent in a die under conditions of 0 friction, okay, and 0 axial tension. Fine. So, that means there is no tension, only moment is given, but you can see that here unit width is not considered. So, you have to be careful. 200 mm wide is given and thickness is given. So, the radius of curvature of the die is 80 mm. Okay. The stress strain relationship is provided by this sigma bar is equal to, sorry, MPa is here, sigma bar is equal to 600 epsilon bar power 0.22 MPa, okay, and the properties are basically E is equal to 200 GPa and Poisson's ratio is 0.3. So, these all are given. What is actually wanted is radius after spring back. So, you need to get the radius of curvature after spring back. Okay. So, basically what we need to do is we need to get del 1 by rho. Okay. We need to get del 1 by rho. So, del 1 by rho, we know this del m divided by E dash I, we know this already. So, what is E dash? 1 by 1 we will calculate it here. So, E dash is nothing but E by 1 minus nu square, right. E is given, nu is given, you can get E dash, you can check calculation. So, now if we want to get del m, which is nothing but our m only, which is nothing but our m only, is given by this equation, m by I n is equal to sigma 1 by y power n is equal to k dash 1 by rho power n. Why this we are taking? Because the material is given, sigma bar is 600 epsilon bar power 0.22, which is a strain hardening material. Okay. So, that is why we are using this equation and I n is given like this. Okay. So, if you want to use this equation, you will see that I n has to be calculated to get delta m. You want delta m, okay. You need to calculate I n and then k dash should be known, okay. And then you have to calculate your 1 by rho. 1 by rho which is already given. 1 by rho is already given for us. Okay. So, I n has to be calculated and k dash have to be calculated, right. So, k dash how do you calculate is by using this relationship. You will see that this is already derived. Sigma is equal to 2 by square root of 3 into sigma bar. For plane strain bending we already derived it. 2 by square root of 3 into 600 epsilon bar. Also we derived 2 by square root of 3 into epsilon power 0.22. 600 is same, 0.22 is same. Instead of epsilon bar, you are putting 2 by square root of 3 into epsilon. This also we derived for plane strain bending. If you calculate it, it will be 715 epsilon power 0.22. Please check. This is going to be your k dash. This 715 MPa is going to be your k dash. In a normal sense, sigma is equal to k epsilon power n we use. So, now what we have done is we have converted that sigma bar is equal to k epsilon power n, k epsilon power n. This has been converted to plane strain bending situation as shown here. by using this particular Steinhorning law. So, which means that this is not K, this is actually K dash. So, K dash has been found out, not a problem. So, now what we need to get it is IN. So, IN is already given here, T power n plus 2 divided by n plus 2 into 2n plus 1. Only thing is, in this it is considered as unit width, but the width is given as 200 mm. So, you need to have W also here, which should be considered somehow, and that is why I put a circle here. You can see by substituting all the known values in this equation, you will get this particular value. So, 0.2, which is nothing but my width, into 2 into 10 power minus 3 power n plus 2, which is 2 plus 0.2, 2.22, units have to be consistent, check it. So, n plus 2 again this, 2 power n plus 1 is this. So, finally, I will get IN as this. So, from there I can calculate this m as IN into K dash into 1 by rho power n. So, IN is nothing but 3.94 10 power minus 8, K dash is 715 into 10 power 6 we keep, okay, unit consistent. Then 1 by rho power n is nothing but this is 80 mm. So, 80 mm again unit has to be consistent, 0.08 power 0.22. If we check it, it will be 49.1, okay, m we will get. So, that you can substitute in this equation. So, del 1 by rho is nothing but del m divided by E dash I. So, all are known to us now. E dash already obtained, 219.8 GPa, I we can calculate, which is nothing but W T cube by 12 here. You have to be careful, it is T cube by 12 for unit width, but it will be W T cube by 12 in this particular case because W is given. Del m is nothing but your m, which you already know. Okay, we can substitute all these things. So, you can see that 49.1, okay, divided by 219.8 into 10 power 9, okay, and I is nothing but T cube by 12, W T cube by 12. So, W is here, T cube is here, 12 goes to numerator. Finally, you will get del 1 by rho as 1.675 meter inverse, right. So, this is only del, okay, del 1 by rho. So, now final curvature, how do you get it? You can get it by 1 by 0.8, which is again the original radius of curvature. This is what actually references, okay. We need to bend a sheet to this much of radius of curvature. So, but then it is not going to happen. We are going to remove this particular part from this, which already calculated, which is about 10.8 meter inverse. And if you want to get radius of curvature, okay, so you can take 1 by 10.8, which is nothing but 0.093 meter. Just check the units consistently, okay. So, you can also convert into millimeter if you want. So, just check the units consistently. Finally, radius of curvature is obtained in this way, which is what has been asked from us, okay. So, this is question number 3 because we worked out 2 problems before, okay. Question number 1 and 2 we solved in between also, okay, we have done it. So, this way you can calculate spring back using simple equations. So, del 1 by rho is what we need to get. So, all other things are calculations responsible for your del m, E dash and I, okay. So, instead of this test strain behavior, I can give a different stress strain behavior, okay. Maybe I can include a temperature also in this, and spring back the bending is done at a different temperature, we can say, okay, and then the equation can change, all the values can change and one can compare also. Okay. So, now let us go to the last section in bending. So, we are going to now demonstrate if you include stretching also what will happen, which is what we are going to call bending with stretching, okay, bending with stretching or bending with tension, okay. But in this what we are actually going to do is we are going to consider a case similar to a stamping operation. Stamping operation means a forming operation, okay. Suppose you are making a large curvature, okay, you want to make a large shed, something like that, okay. So, similar to a stamping operation where the sheet is first curved elastically to the shape of the die and then tension is applied, okay. So, what you do is you actually wrap the sheet on the die, okay, by giving some elastic deformation and then you apply tension. That is the way we are actually going to do. So, bending first and then stretching over a die with a large rho knot, the large curvature, and that situation is given here. You can see this is your die, let us say, and this is your sheet. So, on that die you are actually clamping it and you are giving a curvature to that sheet, Okay. But you are first bending it without providing tension so that the shape is attained, and then you are going to stretch the sheet to get a full shape, and it is a frictionless case. Okay. So, moment is given and tension is given. So, in this situation your stress distribution, okay, can be drawn in 5 different stages, okay, from A, B, C, D, E you will see, and in these cases A is actually without tension, that is your initial stage. B to E is basically the second stage, but at different levels if you provide with tension, because we first said that you are going to give only bending, that means only moment is given, okay, then you are going to pull it to create a full shape. Okay. So, if you quickly observe what is going to happen here, this is a stress distribution, okay, all are sigma 1 only. Okay. So, the first A case is known to you because there is no tension, only moment is given. So, it will be 0 at the center. Okay. This we already discussed, and then we evaluated this stress distribution, it is done. So, now when you provide some tension, little bit small tension is applied, you will see that it is going to go down, your neutral axis is to go down. This also we evaluated, this contains epsilon A and epsilon B. The B part contains epsilon A and epsilon B. Right. So, now C, D, E are further stages of providing tension. Okay. C is little specific. Why? Because you are providing tension such that your plane strain yield stress is reached at the upper surface, okay, at the upper surface, and if you further progress it, the plastic deformation region will propagate throughout the section. So, you see that S is here, now S is up to this particular thickness. Now, in the last case you will see the section is fully plastic, so that your S flow stress is reached fully in the throughout the section. This is T, this is your sheet thickness, this is your sheet thickness. Okay. So, only tension, only moment is A, you just provide some tension. B, increase the tension so that the upper surface reaches S flow stress, nothing but the yield stress. Then with further progress you will see that the S will propagate in the section, this is a elastic to plastic transition, and then here you will have fully plastic section. These are the differences between A to A, B, C and D and E. Okay. So, which is what is we are going to provide details to each one of this, we will quickly do one after another. Initially when the moment is applied without any tension, okay, the stress distribution will be shown in A. Okay. So, now here the strain at any distance, let us say y, from the middle surface is given by epsilon 1 is equal to y by rho, actually ln of 1 plus y by rho, which is written as y by rho. Okay. Since the radius of curvature is rho naught, I am going to write rho naught here, epsilon 1 is equal to y by rho naught. So, for this stress distribution we can get stress distribution is nothing but E dash into epsilon 1, E dash into epsilon 1. So, in this case, okay, it is nothing but y by rho naught only. So, E dash into y by rho naught. Okay. And if you want to get slope of this particular stress distribution, we can get d sigma 1 by dy, which is nothing but our E dash by rho naught only, nothing but by E dash by rho naught. The stress distribution is given by sigma 1 is equal to E dash by rho naught. Okay. Material is in elastic state only, which has got a slope of d sigma 1 by y is equal to E dash by rho naught. That is done. So, let us go to next stage. Figure B to E shows stages when tension is applied and it decreased further, and it increased further. So, we apply tension and then slowly increase it, that is what is shown in figure B to E. B to E, this is what is shown. Now, let us go to specific stages B and C. B and C stages shows stages in which slope remains constant and tension increases, correct. So, this slope will remain constant, only thing is your tension will keep on increasing so that you are going to reach S. So, we are going to say that the initial moment when t is equal to 0, okay, when t is equal to 0 is given by m is equal to E dash t cube by 12 into 1 by rho naught, which is nothing but m naught. This we already know, we derived it. Okay. So, if you want to know that, you can go back and check initial moment, that is t is equal to 0. So, only moment, this we already calculated. Okay. So, you can go back and check, which will be nothing but I am just denoting it as m naught. This moment will be constant until stage C, okay, is reached or material starts to yield. Okay. This moment will be constant until stage C is reached or material starts to yield, because at C only the material will start yield. Why? Because at the upper surface you will see it is going to reach S, plane strain flow stress. So now we will use this equation later. Now you will see that at stage C the sheet will start deforming plastically when stress at the outer layer reaches the yield stress S. At stage C the sheet will start deforming plastically at the outermost fiber when your sigma 1 reaches S, that we already know. At stages D and E with further tension, plastic deformation zone increases like you have shown here and then shown here also. At E the whole section is fully plastic with S as flow stress, okay, which is what is represented here. Now at this stage, okay, you want to get a tension Ty, that is nothing but S into T, that is nothing but S into T. So the tension applied, okay, to enter into the situation seen in C, okay, you want to cause some yielding. For that, so one tension has to be applied, that is nothing but Ty is nothing but S into T, the original definition. Actually it is sigma 1 into T, but then in this case it is S only, S into T, plane strain flow stress into T. So now what we are going to do is, let us get some details into the stress distribution. Okay, so between B and C, the stress distribution at any location, okay, that is my sigma 1, okay, will have two parts. One is sigma 1A and sigma 1B. This is something new which we have not introduced before. We have introduced only two parts in strain distribution. Now we are saying that the principal stress sigma 1 has got two parts. One is sigma 1A and sigma 1B. Similar one to like previously we discussed. The sigma 1A is nothing but uniform stress at the mid surface. And then there will be an addition of sigma 1B which is meant for bending stress, as in the case of section A, okay, that is stage A. So sigma 1B is nothing but E dash into Y by rho, right, C dash into Y by rho naught. So this we already discussed now, this one, sigma 1 E dash into Y by rho naught. Only thing I am writing it as sigma 1B here, it is specifically sigma 1B, okay. So in this case you will see that of course in the A part, of course the sigma 1A will not be there, sigma 1B will be there, so that is why it is actually at 0 at the center. Okay, so now let us go to the limiting case. Now these two are known to us, okay, let us go to limiting case. For a limiting case C, why C is a limiting case? Because it is going to reach S at the upper surface, the outer layer stress is S, okay. If that is the case, you want to get stress at the middle surface here, you want to get stress at the middle surface, what would be the one? Okay, so I am going to say that, so your sigma 1 is what I want at y is equal to 0 is nothing but my S minus E dash into 1 by rho naught into T by 2, isn't it? So my this S is already there, I am going to remove this E dash into Y by rho naught into T by 2. So E dash into 1 by rho naught into T by 2, I am going to put Y is equal to T by 2 here, okay. So I am going to remove that part from that, okay, so that I will get sigma Y at Y is equal to 0. So at the same time I can get tension on that section, okay. T at Y is equal to 0 is nothing but I will get Ty into 1 minus rho E by rho naught. So what is this? T is for the same thing, see, T is nothing but S into T, okay. S into T means this into T. So ST minus E dash into 1 by rho naught into T square by 2, which is nothing but my T Y is equal to 0. This is what I should get, okay. So and of course you can simplify it in this fashion, okay, and you will get Ty into 1 minus rho E by rho naught, where your rho E is nothing but E dash T divided by 2S and Ty is nothing but ST. Ty is nothing but ST, okay. So you will see that the stress at the middle surface can be obtained by this, and the tension on the section can be obtained by Ty into 1 minus rho E by rho naught, where rho E is given by E dash T divided by 2S and rho naught is actually the original one, and in this Ty is nothing but ST. Okay. So what does this equation tell? Some interpretation we will get let us go to this tension in the section. This equation says that if rho naught is greater than rho e, so rho naught is actually the original value which we need to reach, and rho e is a limiting elastic case. Okay. If this is larger than this, then the applied tension will reach yield tension Ty. So, the applied tension is this and yield tension is Ty. Okay. It will be almost same if your rho naught is going to be very large as compared to rho e. If that is the case, this will automatically reach that. Okay. So, now what will happen is, if your applied tension reaches Ty, then there is no need for moment. The moment will actually get lowered. You do not need to give that much of moment which you gave before, it will be actually lesser than that. That is the main point. So, the moment tension is given, then moment is actually not required, it will be lowered automatically. Okay. So, but now let us go to one important one, that is in the D stage. Let us increase the plastic deformation, okay, and then we will get an interface, elastic to plastic interface. What is that? That is this one. This diagram is shown in this particular figure. At some instance, okay, an elastic plastic interface, EP interface, can be identified at a distance qt by 2 from the mid surface. I am referring to this particular distance qt by 2, qt by 2 distance. So, what is this? This is a stress distribution and this is a strain distribution in an EPP sheet bent to a larger gentle curvature and then stretched. So, rho naught is large and then you are actually stretching it. So, this is already known to us, this particular stress distribution is already known to us. From the middle surface you see that there will be little bit of elastic part above that and then it becomes plastic, and below thickness it is going to be fully elastic only because it has not reached plastic deformation. So, that is the situation. So, this line is actually EP interface. This line is actually EP interface. The corresponding strain distribution is shown here. Okay. So, of course, this plastic portion, this shaded region and this shaded region are same. So, here you will see that at the mid location there will be some epsilon A and there will be an additional component of epsilon B, which is nothing but y by rho when you move from middle surface to upper surface. When you move from middle surface to upper surface along y, there will be epsilon A plus some part of epsilon B when you reach the upper surface, and once you cross a particular value, let us say qt by 2, you are in plastic part. That is this part, which is what is shown here. Okay. So, now this EP interface is going to be very important for us because at this particular stage S is known to us. It is sigma 1 is equal to S. Okay. Sigma 1 is equal to S. So, now what will happen if you provide more details into epsilon 1 when you have elastic to plastic transit? This is your EP interface in terms of strain distribution. So, now what details can we provide in that? So, at some instance an EP interface can be identified at a distance qt by 2 from the mid surface, right. So, now in general strain can be written as epsilon 1 is nothing but epsilon A plus epsilon B. Epsilon B is nothing but ln of 1 plus y by rho, which is nothing but y by rho only, which we discussed before itself. So, which is one of the epsilon A plus y into 1 by rho naught, I am just keeping. Okay. So, now what I am going to do is at y is equal to q by 2 distance, that means at the EP interface, epsilon 1 is nothing but the yield strain S by E dash. So, I am going to this particular interface, beyond that I am going to have plastic deformation, means at this interface, okay, epsilon 1 is nothing but my yield strain S by E dash. Okay, basically S is equal to E dash into epsilon 1. So, my yield strain is nothing but now S by E dash. Okay, so what I am going to do now is I am going to equate this epsilon 1 to S by E dash, and then I am going to get epsilon A, and then I am going to get epsilon A, which is at the middle surface. So, what is the value? Epsilon A is nothing but S by E dash minus 1 by rho naught, and this y is a specific case of qt by 2, which is what I have given here. Okay. So, I am going to say that the epsilon A is nothing but epsilon 1, which is 1 minus y into y by 1 by rho naught. Epsilon 1 is nothing but S by E dash, okay, because it is at qt by 2. It is at qt by 2 we are saying, okay, that would be my S by E dash, that will be my yield strain. So, minus 1 by rho naught. In place of what is it, my y, I am writing qt by 2 here. So, I am going to get epsilon A. This epsilon A is actually plotted at the mid surface here. So, now what I am going to do? I am going to substitute this epsilon A into this equation, and I am going to get in general epsilon 1, the strain at y distance from the mid surface, okay, in this situation, that is your D. This is D part, D stage, no? This is D stage. In D stage, the strain at y distance is given by epsilon A plus epsilon B. Epsilon A we derived as this, S by E dash minus 1 by rho qt by 2. Epsilon B is original definition, y by rho naught. This would be your epsilon 1 distribution for D stage. Okay. So, the stress distribution for this stage is actually very easy for us. So, sigma 1 you need to get, which is nothing but E dash into epsilon A plus epsilon B. Okay. So, which is nothing but my S minus E dash by rho naught in qt by 2 minus y, which I can get directly. Okay. So, this epsilon A and epsilon B are already known to you from the previous slide. You can substitute it and you can find out, okay, which is nothing but S minus E dash by rho naught into qt by 2 minus y will come. So, in this way the elastic state can be applied. So, the elastic part. After this it is S, that is known, but how is it going to vary? Okay, we can get. So, now what we are going to do is basically moment and then tension. These two we are going to evaluate. How we will going to evaluate is known. M is nothing but integral sigma 1 y dy and T is right. So, only thing is limit we have to be careful because something is changing. So, what I am going to do is this moment is integral. So, there are two locations. This would be minus t by 2 to qt by 2. This will be 1, okay, and qt by 2 to t by 2 would be my another one. That is what I have given here. So, minus Ts by 2 to qt by 2 is a limit. Within that sigma 1 y dy will come. That sigma 1 is nothing but this one. So, this entire thing is nothing but my sigma 1 S minus E dash by rho naught into qt by 2 minus y into y dy. Okay. After that, okay, my qt by 2 to t by 2 is nothing but S only. Sigma 1 is nothing but S. So, this is nothing but my S. So, S into y dy qt by 2 to t by 2. These limits have to be careful. So, you can simplify this and finally, you will see that your M is nothing but M naught. M naught we already evaluated it. M naught is this. Where is that? This one. E dash t cube by 12 into 1 by rho naught. M naught into 2 plus 3q minus q cube divided by 4. This is what you will get as M. So, then what do you get as applied tension? The same thing, minus t by 2 to qt by 2. Only thing y will not come here. Okay. S minus E dash by rho naught into qt by 2 minus y, which is nothing but my sigma 1, and here it is S only, that is also sigma 1. Okay. So, which reduces to this simple equation, T is equal to Ty into 1 minus 1 by 4 ρe by rho naught into q plus 1 the whole square. That is the way it is going to come. You can check it. What is Ty? We already derived it. Ty is nothing but your tension at yield, which is nothing but St. You can check it. Okay. And in this case, if you want to relate M and T, okay, because we are applying both, right. First actually moment is applied. Okay. So, when tension is 0, x axis is 0, only moment is applied. How much? M naught. Okay. How much? That is your M naught. M naught we already calculated. That much amount of moment is applied. Okay. Just to give some shape to it, and after that the full shape is given by providing tension, and if you increase tension from 0 to Ty, okay, you will see that after the elastic part moment is not required at all. Moment will come down and it will decay to 0 when T reaches Ty. So, when T reaches, tension reaches Ty, you will see that moment is going to be 0 only, and between this elastic to plastic, this particular region is very important for us. Okay. Particular region is very important for us, and in this actually is going to tell you something which is responsible for spring back control. Okay. So, we know that spring back is actually proportional to change in moment, that we already discussed. Okay, your spring back we already related change in moment, okay, to your del 1 by rho, which we already discussed, which means that spring back is proportional to change in moment actually. If the moment in loaded condition is reduced to 0, moment in loaded condition is reduced to 0 by applying yield tension, let us say Ty, this is your Ty, the spring back on unloading would be 0. The spring back on unloading would be 0 because the change in moment is not there at all. So, spring back proportionally will come down. Okay. It also means that applying yield tension will set the shape in the sheet to that of the die. So, if you provide some yield tension, it will actually provide nice shape to the sheet as per what you have in the die. Okay. So, in actual stamping, what you can do is by providing small plastic strain throughout, okay, will ensure negligible spring back. Okay. So, you provide small plastic strain, okay, let us say it can be created by Ty, okay, you provide, you convert tension into yield tension, you push it forward in that way, then small amount of plastic strain can be provided, okay, throughout the section, and hence you will have negligible spring back. So, this interpretation can be obtained from this. This is one way to control spring back. How? In actual stamping you need to provide small plastic strain, okay, with the help of tension, okay, so that you will have a negligible spring back. So, with this we stop here, we will look into next module later.